If we use static information flow analysis, we basically analyze all the possible programs that can run, and we have a glimpse of what's going on inside here, and we can make that decision. Static information flow analysis is concerned with analyzing the source code of a program and then determine how information actually flows. But it's limited in the respect that you can only execute those programs that you have analyzed on the system in order to make a good case. And this might not be acceptable in every situation. Then there's dynamic information flow analysis, and usually dynamic information flow analysis is concerned with actually looking inside of this entity here and trying to figure out what's going on. Because the problem, if you treat that as a black box and you don't know anything what's going on inside and you only can observe inputs and outputs, it is actually undecidable to make a statement whether input 1 or input 2 is responsible for the output. So my hypothesis is that I don't want to find out what's going on in here because this is expensive as well in terms of performance and maybe storage requirements. So my idea is I don't care which of these two is responsible for the output. I'm just going to say both of them are. And therefore, my idea is to bind a meaningful label to a principal on the system, such as here, and then propagate this label as information is being exchanged to other principals or objects on the system. And the actual nature of the label right now is not important. I'm going to go to that in the case studies a little bit. Now, this graphic is a little bit misleading because it makes you think maybe that it was I2 that caused this output. In essence, it might have been I1, and this is where false information gets propagated to. Even if there's not a label associated with that principal there, it might have actually been I1 who caused this output. In this case, A is not really the way the information was truly propagated, but it could have been I2. And this is important information as I will show later for an investigator. So basically, input and outputs are conveyed through channels on the system. If you have principals communicating with each other, and I'm just going to quickly address what Lamson defines for his 3 categories of channels. You have data channels, which are regular channels where you read and write to, and they're intended for information exchange on the system. This can be reading, writing to a file, to a pipe, to a socket on the system, all those things. Then we have storage channels. Storage channels utilize shared resources on a system to convey information. And this could only be as small as 1 bit at a time. And an example of this is testing for the existence of a file. If 2 parties have a shared file somewhere and you agree on certain time intervals to check whether the file is there or not. So in time interval 1, first party creates the file, second party reads it, that's the 1 bit. Next time interval, maybe he deletes it, checks it's not there anymore, that would be the 0 bit. So you can convey 1 bit of information in each time interval that way. And this is what Lamson calls a storage channel. And then there are covert channels, which are channels that are not intended to convey information at all on a system. And this could be things like increasing and measuring system load. And you can use the same kind of example in each time interval. If a user generates a lot of system load and the other one measures it, that's the 1 bit, and if there's no extra system activity, that's a 0 bit. And those are covert channels. The data and storage channels you can determine on a system by using a shared resource matrix. And that was proposed by Kimmerer, and I'm not getting into that in any more detail. So basically, you can identify those channels. Whereas for covert channels, it's usually not that easy to do so. And I will not consider covert channels any in the remainder of this work. So, given that I want to bind a label to a principal and then propagate it, I have a basic model. We have a set of labels, a set of active principals, and a set of objects and channels between principals and principals, as well as principals and objects. There are label sets associated with all the principals, the objects, and the channels themselves. And we have some sort of update function that updates labels as information is being exchanged. I have the following operations, and I'm not going to go into too much detail here. Basically, we have the adding of a label, the creation of our subjects on the system. Then we have opening and closing of channels, as well as reading and writing to and from them, and we can destroy principals and objects. So during each of those operations, the label sets of the involved parties might or might not have to be updated. For example, if you open up an object for reading, which the notation here is that the information flows from the first parameter to the second. So open OP would be opening the channel for reading, so P can read from O. So if you do that, then you need to update, for example, the principal's label set with the objects. But the object's label set is not affected at all because nothing has happened to the contents of the object yet. If you write to a channel, for example, nothing happens if it's a channel between principals, because the channel gets the label set of the writing process, but the other principal is not updated yet because it's an asynchronous operation, and you're basically writing into a pipe, and only when that information is read again, we update the label set of the second principal. And probably this example is going to make it a little bit clearer, and I hope that gets recorded okay. So we have this set of operations here. We have an initial state with 4 principals. First, P1's label set is A, P3's label set is B. Plus we have one object on the system whose label set is C. And as my update function, I'm simply using the label, the set union operator. So we're just unioning labels as we go along. So we have the following operations. Principal 1 creates an object O2, at which point O2 inherits the label set from its principal. Then a write channel is opened and data is written to that object, and the channel is closed. Now P2 opens a reading channel to the object 2, at which point P2 inherits the label from the object, label A. And he reads opens the channel, reads from the object, and closes the channel. Then P1 gets rid of O2, so there's no more O2 on the system. Now P2 creates a new principal who inherits the label set of P2, which is A. P5, the newly created principal, now opens object O1, who had label set C and therefore inherits the label set, reads data, closes the channel. Now channel between process P3 and P5 is opened. So P5 also inherits label B from P3. P3 writes some data to P5, which P5 then reads, and then the channel is closed. And finally, a channel between P5 and the principal P4 is opened, at which point P4 inherits all the labels from P5, and data is written to P5. So you might say, big deal, what does that all mean? So, and just to make sure I don't screw this up,